Good morning everybody. My name is Alex Koshi. I am the TA for the course Phase Equilibrium Thermodynamics. So today I will be discussing a few problems that deals with the contents of week 5 of this course. There are a couple of problems that deals with the fugacity coefficient estimation, and there is one problem after that that deals with the estimation of molar volume of a mixture from Amagat's law as well as from Dalton's law. So let me go to the problems first of all. So the first problem, I am going to read it out. Estimate the fugacity of propane at 60 degrees Celsius and 17.03 bar. Use the generalized compressibility factor correlation and Lee-Kessler data. So the critical temperature and critical pressure are given. Tc is equal to 369.9 Kelvin and Pc is equal to 42.57 bar. The eccentric factor is given and it is 0.153. So the first thing that we need to do is we need to list out the values that are given to us. So I am going to do that. T is given, that is 60 degrees Celsius, that is 333.15 Kelvin. Tc, critical temperature, is given and that is 369.9 Kelvin. Pressure is given, that is 17.03 bar. Critical pressure is given 42.57 bar, and eccentric factor is also given 0.153. So the first thing that we need to find out is we need to find out the reduced temperature as well as the reduced pressure using these values. We know the reduced temperature is T by Tc, that is 333.15 divided by 369.9, and I have already calculated these values. I got the value as 0.9, and then I calculated PR, that is reduced pressure, 17.03 divided by 42.57, that is 0.4. So we have the value of TR, we have the value of PR. Now from Lee-Kessler chart we need to find out the value of log 1050, where phi is the fugacity coefficient. So we take this graph. Here in the x-axis reduced pressure is plotted and all these lines corresponds to different values of reduced temperature. So here we know that our reduced temperature value is 0.9 and reduced pressure value is 0.4. So we start from 0.4, we start going up, and when we reaches the reduced temperature line of 0.9 we stop, and then we go horizontally to the log 50 value, and we got log 50 value as minus 0.086. So we keep that value there. Now as we are using a 3-parameter model, we need to find out the log 51 value as well. So we go to the next chart. Here we are having reduced pressure 0.4, we go up, we reach the reduced temperature line 0.9 and we go horizontally, and we get the value of log 51 around say -0.039. So we got log 50 value, we got log 51 value. So we need to find log 5 value, that is log 50 plus omega, that is eccentric factor, which is equal to, and omega value we already know, we have written it down here, so we write that value here. So we get the value of log 5 as minus 9.1967 into 10 raised to minus 2. So we all know how to find an antilog of a value using a calculator. So we find the antilog of this value and we get the value of phi as 0.809. Now we know phi, that is the fugacity coefficient, is nothing but the ratio of F, that is fugacity by pressure. Therefore fugacity that we need to estimate, fugacity is equal to phi into pressure. We know the value of phi 0.809 and we know the value of pressure that is given earlier, 42.57 bar. So solving this, we get the value of fugacity F as 13.78 bar. All right. I'm sorry about this value. This is critical pressure. So the pressure that is given, the pressure of the system is 17.03 bar. So we substitute it here, 17.03 phi into P, that we get as 13.78 bar. Okay. So what have we done here? In this problem, we first of all listed out the values that we have. We listed out temperature, we listed out pressure. We know the values of critical temperature and critical pressure. From these values, we found out the reduced temperature as well as the reduced pressure. And from the values of reduced temperature and reduced pressure, we found out log phi 1 and log phi 0. And from these values, using the eccentric factor value, we found out log phi. And from the value of log phi, we take the antilog and we found out the value of phi. And from the value of phi, we just found out the value of fugacity by multiplying phi with the pressure. So I am going to do a similar problem. That's our second problem. I am going to read out the problem. Determine the fugacity of methane at 32 degrees Celsius and 9.28 bar using the generalized compressibility factor correlation. The TC, PC and eccentric factor values are given. So we proceed in the same way we did in the last problem. First thing, we write down the values. T is equal to 32 degrees Celsius, that is 190, that is 305.15 Kelvin. P 9.28 bar. TC 190.7 Kelvin. PC 46.41 bar and the eccentric factor 0.011. Okay. Now we calculate the reduced temperature and reduced pressure values. Reduced temperature value, we got it as 1.6. Reduced pressure value, we got it as 0.2. Now we have the reduced temperature value, we have the reduced pressure value. So we go to the chart. We proceed from reduced pressure value, that is 0.2. We go up. Now we know that the value of reduced temperature is 1.6. So we need to find out the line for 1.6 here. It is this line. So it means somewhere here. Then we go horizontally to left. So we get the value of log phi 0. We get the value of log phi 0 as minus 0.006. And in the same way, we need to find out the value of log phi 1. We go to the next chart. We start from point 2, that is this point. So 1.6 curve is here and it meets somewhere here, and we get the value of log phi 1 as .007. So we know these two values. We know the value of eccentric factor. So log phi and we get the final value of log phi as minus 5.923 into 10 raised to minus 3. We take the antilog, so we get the value of phi as 0.9865, and we find out the fugacity as phi into p as we did in the last problem, and that is 0.9865 into 9.28 is equal to 9.155 bar. That's the value that we got. So we have almost familiarized with what we need to do when we get charts and when we get reduced means temperature and critical temperature values, etc., to find out the fugacity and fugacity coefficient. So we move on to the next problem. I read out the problem. Estimate the molar volume of a mixture of 40 mole percent propane and 60 mole percent N-pentane at 500 Kelvin and 50 bar using 1 Avogadro's law, 2 Dalton's law. So the values of critical temperature, critical pressure and eccentric factor all are given. We don't need eccentric factor here because we are dealing with 2 parameter model. So we simply avoid these values. So before going into the problem, we need it has been already taught, but I just want to revise it a little bit so that you will be understanding this problem better. We want to look back to what is Avogadro's law and what is Dalton's law. So Avogadro's law of additive volume state that the total volume of a mixture of ideal gases equals the sum of volumes of pure components at the same temperature and pressure as that of the mixture. So basically it means the total volume of the mixture Vm, it is summation of molar volumes of each components, means the volumes of each component that constitutes the mixture. So we can write Zm, that is a compressibility factor of the mixture, as P Vm by N RT, where N is the total number of moles. We can substitute the value of Vm here. And now here instead of Vi we can write so we can substitute this value of Vi here. Therefore mixture compressibility factor becomes this RT and this RT cancels out, this P and this P cancels out, this N comes into the summation part. We know Ni by N is nothing but the mole fraction of the component in the gas. So I am writing it fresh here. Here this is the compressibility factor of each constituent of that constitutes the mixture, and here Zi is calculated at the same temperature and same pressure as that of the mixture, where Zm is calculated. So let me go to the problem. Here we are having we are given temperature is 500 Kelvin. We are given pressure, it is 50 bar. We are given critical temperature, of component 1. I have mentioned propane as component 1 and N-pentane as component 2. So critical temperature of component 1 is 369.9, component 2 is 469.8. Critical pressure of component 1 is 42.57 and that of component 2 is 33.75. Okay, so we need to find out the reduced temperatures and reduced pressures of both these components. But 369.9 is the critical temperature of the first component. We get the value as 1.35. PR1 is equal to 50 by 42.57. We get the value as 1.175. TR2 is equal to 500 divided by 469.8, that is 1.06. PR2 is equal to 50 by 33.75, that is 1.482. So we got the value of TR1, TR2, PR1 and PR2. So now we have a chart, and from there we need to find the value of Z1 and Z2. This is the chart. Here the reduced pressure is plotted at the x-axis, and all these lines corresponds different reduced temperatures, and the y-axis is Z. It's actually Z0, but since we are dealing with two parameter model, I simply mention it as Z. So we need to find out Z1 and Z2 for both components. So here we know TR1 is 1.35 and PR1 is 1.175. So in the same way that we have done in the last problem, we just find out the value of Z1 from this graph. 1.175 will come somewhere here. We go up, 1.35, that is the value of reduced temperature, is coming somewhere here. So we get the value of Z1 as I have made a small mistake here, it will come somewhere over here. So the value of Z1 is 0.84. In the similar way, we calculate the value of Z2 from the values of critical temperature and critical pressure for component 2, and the value of Z2 we got it as 0.35. So here we know we have proved it earlier. For Amagat's law, Zm is equal to summation of Yi and Zi. Here Y1 here we know mole percent of propane is 40 and mole percent of N-pentane is 60. So Y1 is 0.4 and Y2 is 0.6. So we simply do the summation here, 0.4 into 0.84 plus 0.6 into 0.35, and we get the value of Zm as 0.546. Now we need to find out the molar volume of the mixture. We know Vm is equal to Zm into R into T by P. So we know all the values, P T, R and everything we know. We just substitute the values. The value of P is 50 bar. We need to calculate in SI units. We need to put it in SI units. So we write it in pascals, 50 into 10 raised to 5 Pascal. So we get the value of Vm. Value of Vm that is measured is 4.539. into 10 raised to minus 4 meter cube per mole. Okay. Now we need to go to the second part of the problem, that is the estimation of the molar volume of mixture using Dalton's law. So Dalton's law of additive pressures states that the total pressure exerted by the gas mixture is the sum of the partial pressures of its constituents. So what are we doing here? Total pressure of the mixture exerted by the gas mixture is the summation of the partial pressures, Pi. So Zm we know it is Pmv by nRT, which is equal to V by nRT. We substitute the value of Pm here. And we bring these values inside the summation part. Here we multiply both the numerator and denominator with an Ni, and then we rearrange this term. So we know this term corresponds to, I am going over here, over the next page. This term we know it corresponds to Zi, and Ni by n it corresponds to Yi, that is the mole fraction. So similarly we get almost a same expression that we got in Amagat's law. In Amagat's law we got the means we got something like this, but in Amagat's law the Zi that is calculated was at the same temperature and same pressure as that of the mixture, but the Zi calculated in case of Dalton's law, it is at the same temperature as that of the mixture, but it is at a different pressure. The mixture pressure is different, and this Zi is calculated at the pure component pressures. So we move into the problems. So before starting we need to estimate the values of Z1 and Z2. So for that we need to know the pure component pressures, but that we don't know. So as an initial guess we take the pure component pressures as the partial pressures of each component. So P1, I am just writing it in a tabular form. So P1 we take it as the partial pressure of the component, that is our initial guess. That is 20 bar, and P2 is 0.6 into 50, that is 30 bar. So we take those as our initial guess for pure component pressures. Now we know the PC value, we know the TC value, everything. So T, our reduced temperature value, is same as that of the one we measured for the Amagat's law case, that is 500 by 369.9. This is the critical temperature. So that we got as 1.35. Now using these values, these P1 and P2 values, we know the PC1 and PC2 values. So we find out the PR1 and PR2 values. PR1 value we got it as 20 by 42.57. Now from these values we can calculate Z1 and Z2 using the chart that we have done earlier, so I am not going into it. I am simply writing down the value. Z1 here we got it as 0.94, Z2 we got it as 0.68. So I am writing down the values here. Okay. Now from these values we can calculate Zm, that is 0.4 into 0.94 plus 0.6 into 0.68. We get the Zm value as 0.784. Now we need to calculate Vm. We do it in the same way as we have done for Amagat's law. We know the Zm value, that's 0.784 into R 8.314 into T, that is 500 Kelvin, divided by the total pressure. We get the value of Vm as 6.518 into 10 raised to minus 4 meter cube per mole. I am writing it here. Now I told you earlier, we have assumed that we assume the pure component pressures as the partial pressures of each component. So that was our assumption. We need to cross check whether our assumption was right or wrong. So we need to recalculate P1 value and P2 value using the Z1 and Z2 values that we have got. So I am doing that. P1, you know, it is Z1 N1 RT by V. We assume 1 mole, so Z1 is 0.94. I am taking it from here. N1 is 0.4, R is 8.314 and T is 500 Kelvin, and V, it is a Vm value that we have got from here. It is 6.518 into 10 raised to minus 4. And we get the value of P1 as we get the value as 23.98 bar. I am writing here the value, first iteration. And we get the value of P2 in the similar way. We substitute all these values. Z2 we know it's 0.68, we get the value as 26.02 bar. I'm writing down the value here. So if we just notice, we can find out that here there is a deviation from our initial guess. Around 4 bar deviation is there, 20 to 23.98, and here also around 4 bar deviation is there, 30 to 26.02. So our initial guess was not exact, means it was not very good guess. So we need to recalculate the whole thing with our first iteration values. So we know P1, we know P2, we find out PR1 again, and we find out PR2 again, and from this PR1 and PR2 value we know the TR1 and TR2 values already. That is the initial value itself, there is no change for TR1 and TR2 values, and from these values we use the graph and we find out our Z1 and Z2 again. I am not going deep into the calculation because there is a time limit for me. So I am just writing down the values of Z1 and Z2 as calculated earlier. Z1 value it is 0.93, Z2 value it is 0.773, and we can calculate Zm as I told earlier. Just a minute. So I am writing down the Z1, new Z1 value that I have got, and Vm we know it is 0.81, that is a new value that we have got. So we get a new value for Vm, that is molar volume of the mixture. Write down the value here. So we continue these iterations till we get least deviation between these P, means these P values, that is here we got a deviation of 4 bars. So this deviation reduces with iteration, and finally we have to be satisfied with that point that where this gap has come down to a very small value. Now as we have got the value of Vm after our first iteration, so we need to do our second iteration. So we need to calculate P1 and P2 again from the new values of Z1 and Z2. So I am going to do that here. The new value of Z1 is 0.93. And the new value of Vm is 6.734 into 10 raised to minus 4. And we get the new value of P1 as 22.96 bar. Similarly, we get the new value of P2 as 27.04 bar. So we know the new value of P1, we know the new value of P2. We calculate PR1, PR2 again. The values of TR1 and TR2 are the same that we calculated earlier. So from the chart we can find out the new values for Z1 and Z2. We do that again. So we got the values of Z1 and Z2 as okay, I am writing the values of P1 and P2 here. We did the calculations and we got the value of Z1 as 0.93 and Z2 as 0.73. We did the calculations and we found out the value of Zm as 0.81. And if we just simply compare, we can see that here the value of Z1 is 0.93, here also it is 0.93. 0.73, 0.73, 0.81 and 0.81. So, there is no difference after the second means after the first iteration. When we come to the first iteration to second iteration, there is no difference in these values are exactly the same, and the value of Vm when we calculate it, we get it again as 6.734 into 10 raised to minus 4. So, since there is no difference after this iteration, we fix the value of Vm as 6.734 meter cube per mole. Into 10 raised to minus 4 meter cube per mole. So, this is how we calculate the molar volume of the mixture using Dalton's law. So, in this problem we have found out how we calculate the molar volume of mixture using Amagat's law as well as Dalton's law. So, that is all for this tutorial, and if you are having any doubts regarding these problems, just let us know, we will be helping you. So, that is all. Thank you so much.